Okay, hi everybody. We're back for notes on graphs of logarithms. You worked on this a little bit with the lumberjack activity, but now I'm going to explicitly show you how to graph logarithms and answer some questions. And at the bottom of the page are the detailed notes and reminders for transformations of logarithmic functions. So in the beginning, we've got the graphs of, or the tables for the graphs of 2 to the x and y equals log base 2x. I think you're already, I hope anyway, you're already thinking about the relationship between these two. So here we go. If I use a calculator or Desmos or just my brain to calculate these, I know that 2 raised to the negative 3 is 1 over 8. To the negative 2 is 1 over 4. To the negative 1 is 1 half. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. And 2 cubed is 8. I'm going to go over here and plot those points. Negative 3, 1/8 is awfully hard to graph. Negative 2, 1/4. Negative 1, 1 half, even harder. 0, 1. That's a key point with all exponential functions because anything raised to the 0 will be 1. Over 1 up 2. Over 2, 4. 3, 8. And here in blue is what the graph of 2 to the x looks like. Now in red, we're going to look at the graph of y equals log base 2x. So this is asking, to what exponent do I have to raise 2 to get 1/8? And the answer is negative 3. To what exponent do I have to raise 2 to get 1/4? And the answer is negative 2, negative 1, 0, 1, 2, and 3. What you should be thinking is, hey, there's a relationship between these two tables. And in fact, that will also pan out to be true on the graph. So 1/8 down 3, 1 half down, 1/4 down 2, over 1 half down 1, through the point 1, 0. That is a common point for all logarithmic functions, which you saw in the lumberjack graphing activity. Over 2 up 1, over 4 up 2, and over 8 up 3. Connecting those dots, this is the graph of y equals log base 2x. And again, just labeling this as a graph of y equals 2 to the x. What do you notice about these two functions? Well, I hope that you're going to tell me that you notice that they are a reflection over this line y equals x. When we look at the table of values, we notice that the x and y values are switched or reversed. What do you notice on the graph? Well, as we said, there's a reflection. These two graphs are a reflection over the line y equals x. You're probably ahead of me now. The domain and range for the first graph, well, the domain for the first graph in blue is all x values, x of all real numbers, and the range for the exponential function is all y values that are greater than 0. The domain and range for the second equation in the logarithmic function in red, well, the domain for this function is all x's greater than 0, and the range for this function is all y values. Is all y values, so our answer is all real numbers. I just changed this. That should just say the range. All right, so if all the x and y values are reversed, that means that the domain of the original function and the range of its inverse are going to be the same. So all the x and y values switch, and domain and range switch accordingly. All right, to review at the bottom, these are just the rules for transformations, and they follow all the same rules or logarithms that they do for every other parent function that we've studied: quadratics, absolute value, cubic functions, and exponential functions. So what we're looking at here is when a, the value in front, is a positive number greater than 1, we're looking at a vertical stretch by a factor of whatever a is, 3, 4, 2. When a is less than 1, so when a is a fraction, we're looking at a vertical compression, or in other words, a horizontal stretch by a factor of a. And then, of course, when a is negative, we're looking at a reflection over the x-axis. Now, when h, which is always going to be attached to x, is positive, so when h is positive, we're going to see it shift to the right h units, but what you'll see, remember, is x minus h. That's when h is positive, because the function says subtract. And when I'm subtracting a positive number, I'm going to see a subtraction sign. Now, when h is negative, I'm going to shift, in other words, when it says x minus a negative h, or in other words, x plus h, I'm going to see a shift to the left h units. And now, finally, when I have a plus k, if k is greater than 0, I'm going to see a shift up, and if k is less than 0, I'm going to see a shift down k units. Our vertical asymptote is going to be wherever the h value is, so wherever the function moves left or right, that's going to be where our vertical asymptote is. Our reference point is always this point 1, 0, and then plus h, k. So it moves left or right and then up k units. Depending on what your equation says, you're going to move from that anchor point of 1, 0. And in general, just the reference point b, 1 is where you start, and every point from there is going to be moved h units or k units. H units left or right, and k units up or down.